Let's carry on in Nakov, reading an array from the console. Yes, this is a very important thing that we should note. Whenever we enter values from the console, remember that we enter string values. Now repeat that. This readline method from the console class, that readline method, always returns a string. So if I want to enter numeric values into my array, such as an int, I have to take the string and parse it. And then only can I assign it to an integer value. And okay, so that's the length of my array, and I can instantiate a new array of that length. And then I can loop through an array and put values inside my array every time, reading a value from the keyboard, which is a string, parsing it and assigning it to a value in my array. Of course, if the user now makes a typing error or is stupid for some other reason and types a non-numeric number in there, he will get a runtime error. So this is not good programming. You as a programmer should anticipate any error that a user may make and make provision for invalid entries by either using a try catch or a try parse. Try parse is actually better. But you should make provision, and then if the user made a mistake, you should in your program allow a way of asking him to again enter the value with a kind of friendly message. So important, when we enter values from the console, we enter strings and we have to parse the values. Right, here's an example. If we want to check for a symmetric array, all these arrays are symmetric, 1, 2 to 1, 1, 2, 3 to 1, etc. Let's say we have an array, it's already available, and we now want to check if this array is symmetric or not. We have to return a flag or a value, true or false. So that's a program that enters the value into the array. And now the very important line of code is this one. And this example is also in your list of examples on Blackboard. I think check array symmetry, there we are. So that's the example. So we enter the values into the array. So let's run this program. Enter a positive integer. No, I can't remember what this was. Okay, so that's the number of elements first. So let's say we have 5 elements in the array. Let me just make this a bit bigger. 5 elements of the array, and I can have 2, 3, 2. Sorry, 2. Make it a 3. 2, 3, 3, 3, 2. That's 5 elements. So this is symmetric, and question is symmetric true. It is true. So run another example. So enter a positive integer. Let's put in 5 numbers again. 1, 2, 3, 4, 5. And of course this is not symmetric. So is symmetric question false. So that is what this program does. So this part just put values into the array. And now the very important part is line 24. Line 24. It's like when we go to court, you are not guilty until proven guilty. So we have a flag with an initial value symmetric is true. So we set that flag to an initial value. And then we step through the array, all the elements in the array. Inside there we compare one element with another. If they are not equal, we change the value of the flag. And the moment that we get one false position, there's no need to check more, so we can break out of the loop and then we can write down the final answer. So important thing, we have a flag, symmetric is true. Next important thing, we step through all elements. Is it really necessary to step through all elements? No, it's not. We can only step through the first half of elements. So we step only through the first half of elements, and then what do we compare? Now note this. If I is 0, again we have this little thing inside the index. n minus I minus 1 gives me the index on the other side of the array. If I is a 1, n minus I minus 1 gives me the index on the other side. You can check it yourself and draw a little picture. Maybe I can do it here. And now you must forgive me my drawing abilities. If I have an array, and this is very awkward drawing with a mouse, so you can laugh now and then you're done laughing and then you just concentrate on what I'm doing. So that's my index 0, that's my index 1, that's index 2, that's index 3, and that is index 4. If I have a value here of 4 and a 3 and a 7 and a 3 and a 4, now I want to compare index 0 with index 4. So n in this case is 5. 5 minus I, which is 0, 5 minus I minus 1. So 5 minus I minus 1 gives me a 4. So that compares index 0 with index 4. If I is 1, I say number of elements n minus 1, which is 4 minus another 1 gives me a 3, so that will be index 3 will be compared with index 1, and so on and so on. So this way we compare opposite elements in the array with each other. If they are not equal, then we reverse the value of the flag. Now this principle of this principle of assigning an initial value to a flag and then proving it different somewhere along the way, that we will use quite often. Make sure that we understand that principle. I'm going to close this one, and then we carry on with Nakov. Printing to a console, I don't think that is iteration through elements of an array. Yes, I think I mentioned on Monday the differences between a for loop and a for each. You know the syntax of a for quite well. Just make sure that you understand how this all works and go through it slowly. We don't have time in the class. Now, for each is different than a for in several ways. First of all, it's quicker and faster and to go through elements, but it has a limitation in that we cannot decide what specific elements and the increment and limit the elements that we want to step through. If we say for each, we actually mean for each. But if that is the intention, then for each is faster than a for loop. Okay, so then the next thing is multi-dimensional arrays. Sorry, I see there's a message. Let me just read the message. I think I got that message. All right. Multi-dimensional arrays. Now, there are two ways in which we can define multi-dimensional arrays, either as rectangular arrays or as jagged arrays. And we will see an example of each one of them just now. A rectangular array is declared with that. So it's, again, square brackets with a comma. So that's 2 dimensions, length and width. That's a 3-dimensional one. So you can think of it as a cube or a box or a block. No, not a cube. A cube is equal length, all dimensions. It's a box in different dimensions. So those are examples of it. And this is a 2-dimensional array picture. Index is 0, 1, 2, 3 in one dimension, 0, 1, 2 in another dimension, and that is the content of the elements in my array. So it's typical, can be a checkerboard or a timetable. It's a good example of a 2-dimensional array. A timetable where you have your days on one dimension and the periods in another dimension. So note the hard-coded initialization of data, again, in this way with the curly braces. So that's row 0 values, and that is row 1 values. And there are other examples here. I'm just not going to go into everything detail. It's your job to go in detail through the chapter and make sure that you understand everything. When we print them, we need to go through the array in nested for loops, and that's the important thing. When we have a multidimensional array, we have to go through the array in a nested for loop. So that's one dimension where we go through dimension 0. So the dimensions are numbered from 0, 1, 2, 3 also. And then the next dimension, or then the width, will then be dimension 1. And that's the rows and that's the columns. So we step through the rows, we step through the columns, and we can print now our array. Note the right there and the right line here. That's very important that we understand. So that right will write the different elements of a column. Actually, it should be row there and column there. Should write all those elements, the one after the other, in one long line. And then we have a right line, and then it will move the cursor to the next line, and you will write the next row. Sorry, I was wrong in my comment. That's always happening when I'm teaching. I don't think clearly. I don't necessarily do two things at once. So this is correct. Sorry, I made a mistake in saying it's not correct. This is correct. So for each row, stepping through the rows, then inside a specific row, I step through all the columns, then print everything, all column elements in one long line for a specific row, and then use the right line method to go to the next line, so that when we get the output, it looks like that. That is then the idea. So important when we have a multidimensional array, we need to step through all the elements in nested loops. That's an example of how to read the elements from a console and print them back again. Good. Here's an example in Nakov, and I have this example also in the Visual Studio example in your examples on Blackboard. First of all, the question is, what is the maximal platform in a matrix, or a two-dimensional array? Same thing. So let's say we have a matrix like, is there a picture of this thing? I don't see one, but we can just use this. Let's say we have a matrix like that, rows and columns, and I want to know what subset of 2 by 2 matrix, 2 by 2, inside the bigger one has a maximum sum. So if I say that, and it's difficult to highlight, the 0, 2, can I do it with it? No, I can't. Maybe I can do it. You can try like that. So if I highlight that sub matrix, it's a 2 by 2 matrix, and the sum of all elements in that sub matrix is 10. 2 plus 7 plus 1, that's 10. If I see if I can download, highlight. Okay, let's do this. That I can highlight. If I highlight another square 2 by 2 matrix within the bigger matrix, that sum is 18, 26, 33. So that's 33. Now the question is, what subset, what sub matrix has the highest sum? Now there's a solution, and the discussion is in Nakov. Time will not allow me to go through the entire discussion, but you can go through this solution yourself and the example that's on Blackboard. But basically it says that we should run again through the entire thing, all the rows and all the columns, getting the sum of every specific combination, a row column plus 1, a row plus 1 column, and row plus 1 column plus 1. Those are indexes of a 2 by 2 matrix. Get the sum. If it's larger than the sum at this stage, then replace the sum at this stage with a new sum. So the initial sum is as small as possible, and then see if you can replace it with something that's bigger. So go through this example and understand the principle. What is important to me is to go through the other way of a two-dimensional matrix. I mentioned that we have two types of two-dimensional matrices. The one is a rectangle, and the other one is a jagged array, or so-called array of array. Now, note the difference in declaration. The previous one we declared with a comma between the square brackets. This one we have an array of an array, so it's two sets of square brackets next to each other. So first of all, we declared our jagged array as a thing with it's an int2 with an array in itself. And then the first element of this int array is an int of 5, and the second element is an int of 3. So it's an array of an array. The first element contains two elements, and each one of those two elements contains an array in itself, and they are of different length. They are not of the same length. So there's not a picture here. There's an example. This is my array of array in that heap. So my initial array contains, in this example, 3 elements, indexed 0, 1, and 2. And then this one contains 3, that one contains 3, and this one contains 2 elements. So they are not of the same length, each one of the elements in the first array. So this is an array of array. Now there's another example of how to initialize, and then the all well-known Pascal's triangle example. Let me run my example, which I have here. We first define and understand Pascal triangle. So the Pascal triangle says in the first line we have 1 element, in the second line we have 2, in the third line 3, and in the fourth line 4 elements, etc. Each number, but for the first one, is the sum of the two diagonally above it. So that one is the sum of 0, there's a 0, there's an empty space, and that 1, so there's a 1. If we can take any one somewhere down below here, that 15 is the sum of the 5 and the 10, the two numbers diagonally above it. So we can now forever carry on adding rows, following this definition of every number is the sum of the two diagonally above it. Now this is a way in which we can visualize the Pascal triangle in diagonally, but of course if we take out that line of code, this is how it looks like now. Now it's not it is not diagonal. This is an array 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 arrays in the first dimension, or 12 elements rather. Yeah, 12 arrays, 12 elements in the first dimension, and then each one of these arrays is an array in itself. The first one having 1 element, the second one having 2 elements, the third one having 3 elements, etc. And now if we look how the data is defined, that 3 is the sum of that 1 and 2 there. That 10 is the sum of that 4 and 6 there. So each element is now the sum of the one directly above it and the one above and to its left. And now we just have to calculate the indexes. And by using some index references there, I'm not going to the details here. You will be able to go through this yourself to make sure how we calculate the values of each one of the elements. So the very first elements are initial, and then thereafter we use this definition of above it and to its left. That line there is just a little trick to visualize the thing as a triangle. So take it out and we have it again as a triangle. Sorry, let me just close it and run it again. Then it's a triangle again. Our time is running out. What's next in Nakov? I think we have done a lot of work. Pascal's triangle. Okay, yeah, we're done. We're done. So you can go through Pascal triangles, and then there's some examples here. There's an extra exercise in the material on Blackboard. I think it's number 10. Yes. in the exercises number 10, where is it? There. Write a program which finds the most frequently occurring element in an array. So that's typically in statistics known as the mode of an array. The value occurring the most times. So important that the array is not sorted. So these elements can appear in any order, and there are 1, 2, 3, 4, 5 occurrences of the 5 occurrences of the 4 in this specific example, but of course you can have any example. Now, the take-home message for what we have here for the solution that is available on Blackboard is that a program that works is not necessarily good. I'm going to repeat this. The take-home message of this example is that a program that works is not necessarily a good program. A program must also be efficient. So, if I use this method 1a and I fill it with 100,000 ints, my int is size 100,000, and I step through that array and fill each one of those 100,000 members with a random value in the interval 0 to 99. Now, remember how this rand.next works. It's the lower bound inclusive and the upper bound exclusive. So this thing will fill my array of 100,000 numbers with numbers from 0 to 99, and then I need to find which one of those 100,000 numbers appear the most frequently. If I run it, my first method, I have a timer. Yes, I have a timer class, and this timer will now, it starts there and stops there, and it gives me the time, how long it takes to do this. So if I do it in a bad way, this thing will generate my 100,000 numbers, and now we will have to wait a bit. I checked before the class, I think it takes 15 or 16 seconds to do the job. So let's just wait for it to come back with an answer of how many, of what the number is that appears the most frequently and how many times it appears. There is 18 seconds. The most frequent number is the number 90. And its frequency was 1085. So that was one method. That was the hard code method, method 1a, stepping in a nested loop structure, for outer loop and an inner for and check. I don't have time to go through it in detail. But if I now replace that method 1a with another method doing the same thing, it does exactly the same. It fills the initial array with other values. It does the same thing, and it gets back in 48 milliseconds. It finds an answer by just working cleverer. And even another way of doing it, and this way, in this last example, we sort the numbers. Before we step through the array, we sort it, and then we also get to an answer. You can go through the detail of these methods yourself and make sure that you understand them and how they work. The take-home message: a program that works is not necessarily a good program. It must also be efficient.